Welcome to new session on refraction through lens. In this class we will discuss power of lens, linear magnification and two thin lenses in contact. This concept we will see in detail. Now let us know power of lens. Today's first concept is power of lens. Power of lens. We know that the convex lens converges the ray of light and concave lens diverges the ray of light. Power of lens is the ability of lens to converge or to diverge the ray of light. If the given lens more converges the ray of light, then that lens has more power of lens. If the given convex lens, concave lens diverges the more rays of light, then it has more power of lens. Simply, power of lens is ability of the lens to converge or to diverge the ray of light. How to define power of lens? See here. The ability of convex lens or concave lens? Ability of lens to converge or to diverge the ray of light. Converge or to diverge the rays of light. This ability we are calling power of lens. Look at me. Now this power of lens we will see in other view. How power of lens can define in one more way. Look at me. To understand this, let us take a convex lens. See here. Now simply I will take biconvex lens. This is one convex lens. Right thing. So this is nothing but optical center. Simply shall I take? This is thin convex lens I will take. This is one convex lens, right? Look at me. Once again I will take. This is biconvex lens or simply convex lens. This we are calling optical center. The straight line passing through optical center, that we are calling principal axis. Are you following this? This we are calling principal axis. Now let us take a ray of light incident on the lens and get refracted. How this is? Look at me. Let us take one more ray of light. This is one ray of light incident on the lens and this ray of light can refract like this. Right or wrong? Right or wrong this? Now let us take one more ray of light that is passes through optical center such that this ray of light never deviated, because already we know whenever the ray of light passes through optical center, this ray of light never deviated. How this is? Again, see here. Now let us consider one more ray of light that is passes through optical center such that this ray of light never deviated like this. Are you following me? In this direction this ray of light goes. Right? Now you can take any one object is available. Say this is one object on principal axis. You can take this object as AB. AB is nothing but this object. Now from this optical center, if I draw this line, are you following? So from this optical center, this is somewhat height available. I can take this height is equal to what value? Shall I take this height? Look at me. This is nothing but one line which is passing from optical center such that this height is equal to h. Right or now? In absence of this lens, how this ray of light can travel? This ray of light can travel like this in this direction. And after refraction, where the ray of light can meet? The ray of light meet on principal axis. This point I can call focus. And this is the optical center. Say this optical center is what value? C value. Right or wrong? Now, distance between optical center and principal focus. What we are calling this? This we are calling focal length. Represent by small f. Right things, students. We know that if this angle is theta, this angle theta, then what about this angle? This angle also theta. Now let us see one more meaning of power of lens of the given lens. We know that ability of the lens to converge or to diverge the ray of light, that ability we are calling power of lens. In one more way, how to see? Look at me. So this is one triangle. Which one is triangle? I can take, say, this is nothing but one triangle. I can take this is nothing but n point. So CNCF looks like one triangle. See here. So from this triangle, shall I take sin theta? Which one is triangle? Triangle CNF looks like one triangle. So from this triangle, I can take tan theta. What is tan theta? Tan theta is equal to what value? That is Cn divided by Fc. Cn divided by Fc. What is Cn? Cn is equal to H value. Cn is equal to H value and Fc is equal to what value? Small f value. Right or wrong? Right. Then from this I can define what is power of lens. See here. If the case this height h is equal to 1 value. If the case h is equal to 1 value, then what is remaining? If h is equal to 1 value, then tan theta is equal to what value? 1 divided by f. Where this tan theta is equal to 1 by f and this is equal to power of lens. What I can call power of lens. This power of lens, how to define? One more way. One way, in what way I define? Ability of lens to converge or to diverge the ray of light. That ability we are calling power of lens. But here, power of lens is the tangent of angle. Power of lens is the tangent of angle in which the ray of light falling at a unit distance. The tangent of angle in which the ray of light falling at a unit distance from optical center. If the tangent of ray of light falling at a unit distance from optical center, that becomes power of lens. Simply, the reciprocal of focal length, that we are calling power of lens. Reciprocal of focal length, that we are calling power of lens. This is one way. Or the tangent of angle in which the ray of light falling at a unit distance from optical center, that becomes power of lens. But we know, for a convex lens, focal length is taken to be positive. For convex lens, focal length taken to be positive, so that power of lens can taken to be positive. See here, for convex lens, the power of lens is taken to be positive because focal length of convex lens taken to be positive, right? Similarly, for concave lens, focal length taken to be negative. Already explained in the last class. For concave lens, this power of lens taken to be negative. Then how to take the SI unit? Look at me. The power of lens, actually it is per centimeter or per meter, but we are not using the SI unit. Instead, the SI unit of the power of lens, that is measured in dioptry. SI unit of the power of lens is measured in terms of dioptry. I mean, the power of lens is said to be 1 dioptry if the case the ray of light falling at a unit distance from optical center, that becomes dioptry. See here, this SI unit, how to take? SI unit should be taken in terms of dioptry. It is represented by what value? Smaller value. This is what concept of power of lens. Simply, any lens which able to converge or able to diverge the ray of light, that ability we are calling power of lens. What we know? Smaller the focal length, what is power of lens? More the power of lens. If the lens has less power of lens, lens has less focal length. If less than the focal length, more the ray of light can converge near the lenses. So that becomes power of lens. Mainly, the power of lens, that depends focal length, and again focal length depends on radius of curvature, refractive index, along with radius of curvature. So here, in last class we obtained lens maker's formula. What was the formula here? Lens maker's formula mean what? 1 divided by f is equal to what value? N minus 1 into bracket, how much? 1 divided by R1 minus of 1 divided by R2. Right thing? So that Reciprocal of focal length, that we are calling power of lens. In what way I can define then? P is equal to how much? P is equal to n minus 1 into bracket 1 divided by r1 minus of how much? 1 divided by r2. So that the lens manufacturer use this power of lens to construct a given lens of required focal length to magnify the intensity of the final image. I mean, the human has so many defects, that you are defects of human eye. The defect of human eye can be removed by using the concept of power of lens or by using the lens maker's formula. So this is alternating form of lens maker's formula. This is concept of power of lens. Now let us move one more concept concerned to lens, that we are calling linear magnification. See here. Shall I remove this? From this we will take one more concept, linear magnification. Let us see. Next concept, linear magnification. This concept already we have seen in reflection of light. What is meaning of linear magnification? There, how to say in terms of u and v, and how to say in terms of u and f. That concept already we have seen. Simply, how to define linear magnification? The ratio of size of the image to size of the object, that we are calling linear magnification. Right. Then, in terms of lens, if lens is convex or lens is concave, for that how to take linear magnification, that we will see. See here. Now, to understand this again, let us take a convex lens. See here, this we are calling convex lens. Right thing. This is the optical center. The straight line passing through optical center, that becomes principal axis. Are you following? Now, on principal axis, any one object available. See here, this is one object available. I can take this is one object. Let us take this object has somewhat height. Consider AB is nothing but height of the object, that is represented by O. Right around this. Now, let us consider the ray of light incident and get refracted. How this is? Look at me. This I can call optical center, say it is C value. See here, how it is? Let us take a ray of light incident on the lens, and the ray of light can refract in this direction. After refraction, where the ray of light can meet? After refraction, the ray of light can meet at this point. Now, what we know? One more ray of light that is passes through optical center such that it never deviated. How this is? Look at it. Let us take one more ray of light. How it is? This is one more ray of light like this, never deviated like this. Shall I see this refracted ray one more way? One more way I can see. Look at me. See here. Let this ray of light incident at this point, and after refraction, this ray of light can refract. After refraction, how it comes? It comes like this, remember. Like this it comes. Are you following me? After refraction, how the both rays can meet? The both rays can meet at this point. Shall I take this point? This point I can call A dash. This point I can call A dash. Then, if we join this line, this becomes what? Size of the image. Where it is A dash, B dash represents size of the image. We know that the image of the object AB appeared at I dash, B dash. So that the size of the image can be represented by what value? I. Right around this. Then. See here, simply we will say linear magnification. In what way I can define linear magnification? Linear magnification is ratio of size of image to size of object. Ratio of size of image to size of object. This concept we are calling linear magnification. But linear magnification in terms of u and v, and for convex lens how to take, and for concave lens how to take. I am saying that for convex lens, linear magnification either it is positive or negative. Either it is positive or negative. How it is negative, that will say in terms of u and v. Look at me. In this figure, two triangles are looked like. A, B, C is one triangle, A dash, B dash is another triangle. Are you following me? Two triangles are looks like. What it is? Triangle ABC is one triangle and the triangle A dash B dash C is another triangle. These two triangles are similar. ABC is one triangle, A dash B dash C is another triangle. Both are similar. For similar triangles already we know that ratio height to base becomes constant. What it is from these two triangle? Ratio of heights, that is A dash B dash whole divided by what value? AB is equal to how much? That is B dash C divided by what value? BC. Right or wrong? See here from this figure, distance between optical center to object, that we are calling object distance. This is represented by U, and distance between optical center and image, that we are calling image distance. Shall I take this one? I can take this as V, this as V. See here from sign convention, what we know? From sign convention, simply you can take that. Look at me. From sign convention, this CB is equal to minus U, CB is equal to minus U, and CB dash is equal to V, CB dash is equal to V. Right. By taking this, we will see how linear magnification is negative for convex lens. Look at me. A dash B dash, that is I, AB, that is O, right? B dash C, what is B dash C? B dash C is equal to V divided by what value? Minus U, right? This I can take linear magnification, I by O is equal to M. What it is? Minus V divided by U. Linear magnification for real image. This is a real image. A dash B dash represent real image of the object AB. For a convex lens and the image is real, always linear magnification is negative. For convex lens, when linear magnification is negative, when image is real, for convex lens, linear magnification is negative. Then, how linear magnification is positive for convex lens? For virtual image, always linear magnification is positive for a given convex lens. That we'll see how it is positive. I mean, if the image appeared backside of the lens, that becomes virtual image. Look at me, how it is. Now let us look again convex lens. I will take, this is convex lens, this is convex lens, this is optical center, C is the optical center. Are you following me? Now consider object is situated in between pole and center of curvature. We know for lens, each lens has two principal focus. This is one focus and this is second focus. Remember this point. How it is object situated in between center of curvature and principal focus. So what about this? This I can take AB. AB is nothing but height of the object. AB is height of the object. Are you following me? Consider. If the ray of light incident at this point and after incident the ray of light refract which is passes through principal focus. Are you following me this? Right around. Now let us take one more ray of light. This ray of light which is passes through optical center and doesn't deviate it. Because ray of light passes through optical center, does not deviate it. This refracted ray goes like this. How to produce the refracted ray? If the refracted ray produced in backward side, say this is the refracted ray produced at this point, and this refracted ray produced at this point, where they can meet. So imaginary line, if you produce backward direction, they can meet at A dash. Then if we join this one, this represent what? A dash, B dash represent size of the image. What it is? If AP represents size of object, then A dash B dash represent what value? Size of image. What we know? Distance measured upward perpendicular to principal axis taken to be positive. Right or wrong? Simply I won't be confused anything. Simply I will take linear magnification. How it is? Ratio of size of image to size of object. Upward distance taken to be positive, upward distance taken to be positive. So that linear magnification directly shall I take? Linear magnification is equal to I divided by O. Linear magnification is equal to I by O. I mean linear magnification for virtual image. This is virtual image. Object is here. Image produces behind the object, that we are calling virtual image. And this is size of image. So that if lens is positive and the image is real, linear magnification always negative. But if lens is convex lens and virtual image, for virtual image always linear magnification is what value? Positive value. But if lens is concave lens, always linear magnification is positive. How it is? Again shall I take? I will take concave lens. Look at me. Simply again I will take, this is concave lens. This is concave lens. Are you following me? How linear magnification is positive, that we will see. So this is nothing but a principal axis. What I can draw? This is principal axis. So this is the optical center C. Let us take, this is nothing but object. Let us consider this is one object. Let us take this object is equal to AB and this object has height O. Right thing. Now let us consider this is one ray of light incident. After incident the ray of light can refract in what way? Like this way it can refract. Right or wrong? And one more ray of light that is passes through optical center doesn't deviate it. Right or wrong this? Fine. Let us take one more ray of light incident at this point. After incident it may refract like this, it may refract, or it may refract like this. Look at it. It may refract like this. If the case, this refracted ray producing backward side and this refracted ray producing backward side. Look at it. Where they can meet? They can meet at A dash. Then if we join this line, this represent what? A dash, B dash. A dash, B dash represents size of image. Distance measured upward perpendicular to principal axis taken to be positive. So that how to take linear magnification directly? How to take linear magnification? See here. Linear magnification is what? Ratio of size of image to size of object. Upward distance taken to be positive, upward distance taken to be positive. So that linear magnification is always positive for concave lens, and if the lens is convex lens and image is virtual, so that linear magnification is taken to be positive. Right thing. If the lens is convex lens and image is real, there linear magnification always must be negative. Where the lens is concave lens, always linear magnification is positive. Remember this point. But now we should know linear magnification in terms of U and F, that we'll see. Shall I remove this? Linear magnification in terms of U and F, that concept we'll see, then further we'll move. How to take? See here. Simply we'll see linear magnification in terms of U and F. We know that lens formula is given 1 divided by F is equal to 1 divided by V minus 1 divided by U. Right. Now multiply U on both sides. If you multiply U on both sides, what it becomes? U divided by F is equal to U divided by V minus U divided by U. Right or wrong? Or you can take U divided by F is equal to U divided by V, U divided by V minus 1. Right or wrong this? Or else U divided by V is equal to U divided by F plus 1. Right. Or else U divided by V is equal to U plus F divided by F. Just make it reverse. Reverse mean V divided by U is equal to F divided by U plus F. Where V by U is equal to linear magnification, already we have seen that. Then I can write M is equal to what value? F divided by U plus F. What it is? linear magnification in terms of u and f. Linear magnification in terms of u and f. Now one more we will see, linear magnification in terms of v and f. See here, linear magnification in terms of v and f. Again lens maker's formula, 1 divided by f is equal to 1 divided by v minus 1 divided by u. Now this time multiply v on both sides. V on both sides mean v divided by f is equal to v divided by v minus v divided by u. Are you following me? Or else v divided by f is equal to 1 minus v divided by u, or v divided by u is equal to 1 minus v divided by f, or v divided by u is equal to f minus v divided by v. F minus v divided by f. V by u is equal to linear magnification, then f minus v whole divided by f. What it is? Linear magnification in terms of v and f. What it is? In terms of v and f. In terms of v and f. So this is concept of linear magnification. Now we'll see one more concept, if two thin lenses in contact, that we'll see. Two thin lenses in contact. See here. Next concept is two thin lenses in contact. Okay. Shall I move? Two thin lenses in contact. Two thin lenses in contact. We'll discuss what is the use of two thin lenses in contact. Before that, I will take two convex lenses of different focal length. They placed physically contact such that they have common principal axis. Shall I take here? Now I can take, this is nothing but one convex lens of focal length f1. So this is represented by L1. Right? Now let us take one more convex lens of different focal length. I will take different focal length. One more convex lens of different focal length. So it is represented by what value? L2. The both lenses of focal length f1 and f2 have common principal axis. Both lenses has common principal axis. This is common principal axis. Right around this. Now consider the ray of light incident and get refracted. Ray of light incident and get refracted. How this is? See here. Now consider this nothing but one object situated on the principal axis. From this the ray of light incident. After incident the ray of light get refracted. After refraction it must comes like this. Again at second lens the ray of light can refracted, and after refraction the ray of light can meet on principal axis. This we are calling eye. I mean after refraction the image of the object can appear at eye. Actually this is both having common principal axis, so that distance between common optical center and object is called as object distance, and distance between optical center and image is called as image distance. Right. But the formation of the image can consider in two ways. One way is in absence of lens L2 and in presence of lens L2. If the case the lens L2 is present where the image can appear at eye point, but if the lens L2 is absent where the image can appear, look at me, where the image can appear, Image can appear at some other point. Say image can appear at point I dash. When it is the lens L2 is absent, where the image can appear at I dash point. So that what image you can consider? This image can consider as V dash. Are you following me? Are you following me? Then how to take? Look at me. In absence of lens L2 will take. In absence of lens L2. Look at me. Shall I take? So this lens has focal length how much? F1, and this length has focal length F2. We know initial formula. When lens L2 is absent, where image can appear? Image appear at I dash. Right around this, we know general formula. What is lens formula? 1 divided by F is equal to 1 divided by V minus 1 divided by U. Are you following me? But when your lens L2 is absent, where the image can appear? Image can appear at V is equal to V dash, and same object distance can taken. And the lens L1 has focal length of what value? Lens L1 has focal length of F1. Then what about this equation? This equation can written 1 divided by F is equal to 1 divided by V dash minus 1 divided by U. Let us call equation number 1. Are you following? But whenever lens L2 is also present, where the image can appear? Image can appear at I at what distance? V distance. So that see here, when lens L2 is present, image appeared at I. When image appeared at I, then this I dash is act as object and this is act as image. Are you following me? When lens L2 also present, what it becomes? Image appeared at I. If you stand here, this is act as object and this is act as image. Right on. So again we know equation. What it is? 1 divided by F is equal to 1 divided by V minus 1 divided by U. Right or wrong? Then how the image can appear? Image is appeared at I, it is act as object in this case and this is act as image. So that I can take directly V can be replaced by V only and U can be act as a V dash. So that, and this lens L2 has focal length of what value? F2 value. By taking all these values, what about this equation again then? Shall I write? Look at me. 1 divided by F becomes F2 is equal to 1 divided by V, keep it up same, 1 divided by V dash. Now I can take this is what? Equation number 2. Now combine equation 1 and 2, add equation 1 and 2, what will get? Look at me. 1 divided by F1 plus 1 divided by F2, RHS, 1 divided by V dash minus 1 divided by U plus 1 divided by V minus of 1 divided by V dash. This value get cancelled. What is remaining? 1 divided by V minus 1 divided by U is equal to 1 divided by F1 plus 1 divided by F2. But lens formula we know, 1 by F is equal to 1 by V minus 1 by U. Then what is equivalent focal length? 1 by F is equal to 1 divided by F1 plus 1 divided by F2. Right or wrong? Or 1 by F is equal to what value? P. P is equal to 1 by F1, that is P1. 1 by F2 is equal to P2. Then two convex lens can be added physically. Their power of lens can increase. To converging property of the ray of light, that can increase. So that whenever lens is convex and both convex lens make physically contact, they converge the ray of light near only. the power of lens of both lens can increase. But this equation you can modify. If the one lens is convex lens, second lens is concave lens. For convex lens, focal length are taken to be positive, power of lens taken to be positive. But for concave lens, what is focal length? Negative, power of lens also negative. How it is? Look at it. This is one equation. For second one, how to take? See here, if it is nothing but one convex lens, and simply this is one concave lens. Right or wrong this? This is one concave lens. Both make physically contact. See here, this is what value P1, then what about this one P2? Then what is this value? This value P is equal to how much? P is equal to what value? P1 minus P2. Simply, what is used to make lenses in physical contact? Either to increase power of lens or to decrease power of lens. Two thin lenses contact can be used. This is today's concept. Remaining concept we will see in the next session.